Hello, I'm Nick Hodgson from astrogems.com, and today we're going to discuss the gem identification instrument called the Polariscope. And I've just been looking through my stereo microscope at the blue sapphire on the screen that you can see. And before we launch into the Polariscope, I'd like to just explain the need for gem dealers of today to utilize modern technology to investigate the characteristics of gemstones, their identification, but above all the enhancement techniques that are going on today. Most gemstones in the jewelry store and the high street have been dramatically enhanced, colorized, impregnated with chemicals, heated, gamma nuclear radiated, etc., to such a huge degree that I've noticed in the last 25 years that even though the supply of high quality natural gems is declining dramatically, the cost of gemstones is maintaining a continuum of fairly stable prices, and the reason for that is the massive amount of low quality crystal material coming onto the market that is being heated and cleaned to such a degree that it cosmetically looks very attractive. Having said that, it's important to understand that when you buy gemstones from a person who doesn't understand gem identification instruments and the processes of heat diffusion, treatment, chemical bombardment, etc., that you're probably not buying what would be considered a natural stone. Thank you very much. The gemstone identification instrument called the Polariscope consists essentially of two Polaroid lenses mounted far enough apart to permit transparent gemstones or translucent minerals to be examined between them. Usually the lower plate is fixed while the upper plate can be rotated. It is perhaps the simplest instrument to be used for gemstone identification, but also one of the most important. All gem testing polariscopes operate on the same principle. The gems are examined between two crossed Polaroid lenses, with the vibration direction of the analyzer at right angles to that of the polarizer. This position is the dark or extinction position. When you're in this position, the gemstone is placed on the rotating glass stage. This is a bird's eye view of the gem identification instrument called the Polariscope. It is essentially two Polaroid lenses that has light travel through them from underneath. The lamp is inside the base of the Polariscope. When you turn the top Polaroid lens, you'll see a blinking action as the polymer field is cut into two veins of light at every 90-degree rotation. When you turn it 360 degrees, you will notice that it flashes twice. You turn the Polariscope top lens, the analyzer lens, to a dark field vision. Now you can see very little light coming through the base lens. To understand how polarized light works, it would be important to see that in this sample the principle behind the Polaroid lens. When you look at the top two lenses in the illustration of the polarized parallel axis, you will see that the omnidirectional light waves are traveling through the lenses without obstruction because they're both in the same position. In the lower portion of this illustration, you can see that the second lens is turned at right angles to the first lens, and because it has a crossed polarized axis, the light waves have been extinguished. The same thing happens with the Polariscope when you turn the lower lens at right angles to the upper lens. Another example to show how light waves can be blocked by opposing Polaroid screens is the picture of this gentleman holding a rope that he's vibrating in wave-like formation between the fence posts. The first two are in alignment, and so the waves of the rope are not being disturbed, but the third fence illustration, because it's at right angles to the first two, immediately stops the light waves from continuing. Now that the extinction position has been established, showing no light coming through the bottom polarizer plate, you pick up the glass rotating stage and you can put it on the bottom polarizer plate. These little silver marks were put there just to show when the base platform is being rotated 90 degrees. The first stone that I'm going to show on the Polariscope is a doubly refractive stone. It's a very large peridot. In order to be easy to see, when it is placed on the rotation stage, you'll see the light shining through the stone. When you turn it 90 degrees, you will see a blinking action where it goes from light to dark every 90 degrees. So in 360 degrees, it flashes 4 times light to dark. The second stone is also doubly refractive, and for this sample I have chosen a yellow beryl, which is also a green beryl would be a emerald. And again, when you rotate the raw yellow beryl crystal, it flashes every 90 degrees. This is often called blinking. Gamma radiated topaz, which is blue, again, when it is rotated, it blinks light to dark, light to dark, light to dark. Most gemstones of the crystal group are doubly refractive. It's easier to use fingers with a Polariscope than a pair of tweezers, and you can just rotate the stone this way using your fingers, or if your Polariscope has a rotational platform, you can spin it and check whether it's isotropic, meaning singly refractive, or anisotropic, meaning doubly refractive. And this is a doubly refractive pink tourmaline. On a 90-degree rotation, it blinks once. On a 180-degree rotation, it blinks twice. On 270 degrees rotation, it blinks 3 times. And on the full 360, it's blinked 4 times. And this is a moonstone. And you can see by the rotation how it flashes dark to light, dark to light. That's a simple introduction to the doubly refractive gemstones. Doubly refractive gemstones are known as anisotropic. This is an important term that gemologists have to remember. We've just shown in the previous video how the stone becomes light and dark 4 times through each 360-degree rotation. This is unique to all doubly refractive gemstones, although there can be anomalous diffraction in other stones, so it's not a cardinal rule 100%. Beryl, chrysoberyl, corundum being sapphires, feldspars mostly being moonstone, peridot, quartz, topaz, tourmaline, chrome diopsides, tanzanite, kunzite and zircons are all doubly refractive. Double refraction gems belong to the tetragonal, hexagonal, trigonal, orthorhombic, monoclinic or triclinic crystal systems, and the majority of transparent crystals have double refraction. This image illustrates clearly what refraction is and how it can be doubled in the crystal structure. The surface of the calcite crystal splits light rays into 2 rays, thereby showing double refraction. Each ray will travel at a slightly different speed, which can give a chromatic signature called birefringence. By analyzing the difference between the high and low indices of the doubly refractive gemstone via a microscope, the birefringence can be more easily ascertained. The birefringence and likely identity of the gem can be surmised, though this in turn can be more confirmed with a refractometer as well. No one gemological instrument identifies a stone with 100% assurance. The birefringence of this calcite crystal is known as 0.172. This birefringence table shows a short list of the more commonly known varieties of gemstone in the mineral kingdom. You will notice at the bottom end of the chart the birefringence has a wide reading of 2.87. At the top end it's a very narrow reading. Gemstones with a wide birefringence are more obviously doubly refractive and more easy to see that they are doubly refractive using a loupe or a microscope. The ones that have a very narrow band of birefringence are far more difficult to detect. All birefringent stones are doubly refractive. This photograph shows a single refraction of water and glass. The lower part of the straw is displaced greatly because of the refractive index of the glass and the water. This photograph gives a clear example of the angle of light being changed through single refraction in water. When you follow the straw down to the point of contact with the water, you will notice a slight deviation in the angle. This is another glass crystal that maintains its darkness on the platform. This is a dark pyrope garnet which stays dark throughout all 360 rotations. And here we have a lovely raw spinel crystal which, when rotated again, even though it has many facets at different angles, maintains a dark exposure. And last but not least is a synthetic blue spinel that also stays dark and does not blink through its rotation. Singly refractive gemstones are known amongst gemologists as the isotropic gemstones. When you put an isotropic gemstone on the rotating platform in the dark field on a polariscope, it will not blink. You can rotate it 360 degrees and it will stay dark in all orientations. Garnets, spinels, natural glass, pyrite, fluorite, diamonds that aren't under great internal strain or heavily included, opals and plastics will generally exhibit isotropic phenomena by not blinking on the polariscope. All crystals in the cubic system or isometric system have single refraction and have 3 perpendicular axes of equal length. Common forms are the tetrahedron, cube, octahedron, dodecahedron, trapezohedron, and the hexatahedron. The minority of gemstones in the mineral kingdom have single refraction. And now we're going to move on to the polycrystalline materials, which have a lot of differently orientated microcrystals within their structure. One example here is a chalcedony, which is in this case a light green chrysoprase, and no matter which way you turn it, it stays bright. This is because there are so many microcrystals within the polycrystalline material that no matter which way you turn it, there is orientation for light to travel through the gemstone. Another example would be another agate, which is in this case is a carnelian, and a darker carnelian would be a sard, but this one again you can see light shining through the translucent microcrystalline material. Another example here is a blue lace agate, which shows light shining through at all times. Polycrystalline gems or microcrystalline gems stay light through all 360 degrees of rotation on the polariscope. This is because the orientation of all the microcrystals within the structure of the gemstone will always catch light at whatever angle the gemstone is pointing. Jadeite, nephrite, chalcedony, agates, repeated twin anomalies such as in sapphires, or microcrystalline quartz, ruby doublets, aventurine and sugarlight, all have an excess of orientated microcrystals that allow for light to travel through all directions. Some anomalies can occur even with an isotropic gemstone showing a polycrystalline phenomena because of the excess of inclusions within the gemstone. One example of this would be a lower quality hessnite garnet that has a lot of inclusions pointing in all different orientations. Showing a strain within the stone of strain Anisotropic, often in otherwise isotropic materials. Here is a natural spinel, and this will give a better example of the lines that travel across the stone, showing the strain pressure within the crystal structure. We have a vanille synthetic ruby, flame fusion ruby, and this shows a very good, this sometimes called snake bands that move across the gemstone. Strain Anisotropic shows the anomalous extinction effect often in otherwise isotropic materials. Some almandine garnets, amber, some diamonds, flame fusion or vanille sapphire and spinel, some plastic gems and some fire opal and synthetic opals will show this tendency of the snake bands moving across the surface of the stone in a polariscope. Because of the internal strain within these gemstones, they can be prone to flaking or breaking and have to be handled carefully at the jeweler's workbench. The internal strain of a diamond can be evaluated in a polariscope, which is important if setting it in a challenging jewelry design. The toughness of a material is the maximum amount of energy it can absorb before fracturing, and those gemstones that show strain Anisotropic often need to be handled with much more care by the jeweler in the manufacturing process. Gem dealers should often watch for singly refractive gemstones from the cubic system that show a condition called anomalous double refraction. This is caused by strain within the gemstone, and anomalous double refraction is easy to mistake for double refraction, which is exactly a reason why one needs a dichroscope and a refractometer to confirm this anomaly. It is common in all the isometric gemstones, not very common in diamond, but it can occur, and it is something definitely to watch for. In this image here, with the very large almandine garnet, it also shows a colorized strain pattern that is not visible through a microscope or a regular loupe. I'm not going to go into the details for refining the process of anomalous double refraction because this also includes rotating the upper plate, but suggest for research on this to buy a polariscope and to study from books or your lecturer at a gemological institute. And just for fun, I took this photograph to show another effect I will use when I'm out in the field buying gemstones. When you shine sunlight through a doubly refractive gemstone onto a dark surface, you will often see a doubling of the facets. And if you look at the shadow of my head on this white piece of paper in this photograph, you'll see how the spectral dots appear in twos. And this is evidence of a doubly refractive gemstone. It's particularly easy to see with a peridot or a zircon that have a high birefringence, but in this case I used a peridot. And here I'm holding a garnet and a pair of tweezers, and a garnet is from the cubic system. It's isometric, so it's singly refractive, and as a consequence, when sunshine shines through it, The reflection of the facet edges in a shadow would be just one single dot at a time, and those little white arrows, I hope you can make them out, show just one single dot by themselves. This is partial inference that it is not a doubly refractive stone, but is in fact singly refractive. So in the previous video, which was a basic beginner's introduction to the Polariscope, I'd like to bring up one more reference to the anomalous double refraction stones that we showed, also called ADR. They were singly refractive by nature, but they showed the phenomena of double refraction in the Polariscope, and that anomaly can be overcome in a discriminative investigative identity process by viewing them through a dichroscope. The dichroscope shows the pleochrysm of a gemstone, and that means that you can see two colors of birefringence by looking through the dichroscope, and that will immediately, in a fairly hassle-free manner, identify that the stone is doubly refractive or singly refractive, isotropic. And the dichroscope looks like this. It's very easy to travel with. When you're shown a ruby crystal in the streets of Sri Lanka and you're a little bit suspicious about its identity, you pull out the dichroscope and have a look through it, and if you see two colors through the calcite crystal which was inside it, you know it's a doubly refractive stone, and thereby it's not a pink spinel or red spinel, and it's not a garnet, which are both in the cubic system and both singly refractive. So that's a very important little tool to have with you when you're looking for different birefringent stones. There's a lot of different color signatures that this will give you that over time you'll become familiar with, and it's a lovely little tool, doesn't require any liquids, and it's very small and light and you can travel with it. Having said that, I'd like to go into the point that when you're traveling, visiting different gemstone mining areas of the world, that you need to have a travel gemological ID kit with you. Sometimes you might go back to the hotel and look at the stones you've selected during the day to verify their identity. The Polariscope we've shown is a little bit impractical to take on the road with you, with baggage limitations of travel, etc. And I'm holding here in my hand a travel Polariscope. Has the rotating stage here, it has two Polaroid plates there, two Polaroid plates, and it has a little flashlight that shines the light through the Polariscope. A little bit more tricky to use, but it's more than adequate for being sure of the identity of the gemstones you're buying, along with your refractometer and dichroscope. So that covers that part of the Polariscope. Basically, experience and study will give you far more avenues of investigation. We haven't discussed the conoscope yet, which is an essential tool to be used in relation to the Polariscope, and that's a pretty important instrument. It's very small, again you can travel with it. Here's one example of one of the designs of the conoscope, and a fun tool that helps the gemologist investigate the axis of the crystal structure. The conoscope shows the interference pattern or interference figure, which is generally a pattern of rings caused by optical interference observed when diverging light rays travel through a non-isotropic substance, in other words a doubly refractive substance. It's the best way to determine if a mineral is uniaxial or biaxial, and also for determining the optic sign in optical mineralogy. The observed interference figure essentially shows all the possible birefringence colours at once, including the extinctions in dark bands which are known as isogyros. It's a very handy little tool to use, and again is a sort of a twin sister to the Polariscope. In the future we're going to be producing some more videos, and we'll introduce the conoscope and the dichroscope in some detail then. We really hope you've enjoyed this video, and we plan on doing a testing video to show how developed your skills are in understanding the basic principles we've explained in this video. Thank you very much from the AstroGems Academy online, Nick Hodgson.
Alma says, remember to set apart at least 1 hour every day to do some service for others. While the food we eat nurtures our bodies, it is what we give in charity that nurtures our souls. If time is not available daily, reserve at least a few hours every week for some worthwhile act of charity. Whatever we give it with discrimination.
Paramahansa Yogananda said, life should be chiefly service. Every good action that you perform digs like a pickaxe into the soil of consciousness and brings forth a little spray from the fountain of God's joy. Yogananda was the author of Autobiography We Gave.